Question 3. Glycerol is widely used in the food industry and in pharmaceuticals, but a series of reactions starting from glycerol is shown, and we are seeing everything here. Now you can see that this is a primary alcohol, but it is oxidized to a carboxylic acid. And then the secondary alcohol here goes to a ketone. That means what we are having here is an oxidation reaction. Okay, that's oxidation. And then what else do we have? When we put sodium cyanide and hydrogen cyanide, of course, we are going to form hydroxy nitrides. Okay, so this is an addition reaction. You add the CN here, and then this one becomes an OH, that one there. Okay, then that is that. So they are telling us Roman 1, suggest the reagents and conditions for reaction 1. Remember, for 1 here, it is an oxidation. It's an oxidation reaction. So I look for a stronger oxidizing agent. So I can say acidified potassium dichromate. Potassium dichromate solution, or just dichromate. And then we must heat this one under reflux. Okay, because when we heat it under reflux, remember, when you oxidize this one, the primary alcohol, it is going to go to an aldehyde. Then from the aldehyde, it can proceed to the carboxylic acid. So if you oxidize and you distill, then you are going to get out what we call an aldehyde. But if you continue to heat when nothing is actually escaping, then you oxidize the aldehyde, which is formed further to carboxylic acid. So that's why we say heat under reflux. Okay, then Roman 2, name the reaction mechanism for reaction 2. Okay, for reaction 2, I say this is an addition. So what are you adding there? You are adding a cyanide, which is rich in electrons. Remember, this one is partially positive. This one is partially negative, because this one is more electronegative compared to the carbon. So then this one donates the electrons to this one that appears to have lost electrons, and then this one is broken down. So this one, which is rich in electrons, is a nucleophile. It loves what is in the nucleus. And nucleophile. Phile means love. Then nucleo comes from the nucleus. And in the nucleus, we have protons and neutrons. Protons are positively charged. Neutrons do not have a charge. You get that? So this which loves what is positively charged must be negatively charged or rich in electrons, because electrons cancel out the charges of the protons. You see that? So this is a nucleophile. So what we are going to have here, this one is going to be a reaction which we call nucleophilic addition. So nucleophilic addition. The reaction is an addition one, okay? But then the mechanism is nucleophilic. Remember, we also have nucleophilic substitution, like for example, from halogen alkanes, if I want to get, let's say, alcohols, and then I use aqueous sodium hydroxide. You see that? That is nucleophilic substitution. It can be under maybe SN1 or SN2. Okay. Roman 3. Yes, and give the observation you would make when 2,4-dinitrophenylhydrazine is added to P. So where is P? P here has gotten a ketone, and this one here gives a positive test with ketones or aldehydes. And here we are seeing a ketone, so that means there is a positive test, which is an orange precipitate. Even if you say yellow, some people are colorblind, so this one can be orange, then others can see yellow. So they give, sometimes others even put red to make matters worse. So that is an orange precipitate. Then Roman 4, Q does not show optical isomerism. Optical isomerism, remember, comes into place if we have a chiral center. But that means that carbon must be having 4 different groups that are attached to it. You can see that this carboxyl group is the same as this one here. So it has 2 groups which are the same. So it cannot have the chiral center, and therefore no optical isomerism. So I will say it doesn't have a chiral center. A chiral center. Okay? Or you can say 2 COOH groups. It has 2 COOH groups. You can also write that. So that is that. Then Roman 5, when Q is heated is heated with excess aqueous ethanoic acid in the presence of catalytic amount of sulfuric acid, 2 reactions take place to form compound R. This is compound R. Identify the 2 types of reaction that occur. Okay, now first of all here, we are heating with excess. Let's check out Q. Q, yes, it is here. We are using ethanoic acid, so it comes here. The ethanoic acid reacts with an alcohol, that is esterification. Okay, that is a condensation reaction because a water molecule is going to be lost. So you are going to bring your OH here, okay, for the carboxylic acid. Actually, let me write it like this, like that, COOH, and then CH3. That is the ethanoic acid. So this one, it will lose the OH, and then this one will lose that. So that's why you find that here you have O, okay, then it connects to this carbon here, then OCH3, okay. This O here can come like this here, okay, like that. So you get an ester, in other words. Now, then the other one, we can see that, what else? We are seeing this one going to a carboxylic acid. So the moment you bring an acid and then you react it with a nitrile, you put a nitrile in it, it is going to be hydrolyzed. Okay, then this one goes to a carboxylic acid. So that is what exactly we are seeing here. Okay, so the 2 reactions are, we have hydrolysis, the conversion of the nitrite to the carboxylic acid, and then here we are seeing a condensation reaction. Condensation reaction. Sometimes they also give those ones who say esterification, but you should know it is a condensation reaction. So that is that. Part B, glycerol can be used as a starting material in the manufacture of nitroglycerin. Okay, nitroglycerin decomposes rapidly on heating to form a mixture of gases. This is the one here. A sample of nitroglycerin decomposes, releasing 1 liter, 1.06 decimeters cubed of oxygen at 850 kelvins and 1 times 10 to the power of 5 pascals. Calculate the mass of glycerin that decomposes. Okay, so the fact that here gases are being released, we are going to consider the the ideal gas equation. So PV is equal to nRT. In this equation, they need mass, okay? So if they need mass, then this one is PV, which is equal to M over MR, then T. So mass is therefore going to be equal to PV times MR, okay? Then we shall divide by RT. So now when we are using this equation here, pressure must be in pascals or Newton per meter squared. Remember, pressure is equal to force over area, and force is in newtons, area is in meters squared. So that's why we are saying Newton per meter. Okay, then from there, what else do we have? Volume. Volume must be in meters cubed. If pressure is in Newton per meter squared, volume has to be in meters cubed, and the temperature has to be in kelvins. Now, what we are given here is the volume in decimeters cubed. Now, we need to do that conversion here. 100 centimeters is equivalent to 1 meter, right? So when I cube 100 cubed, centimeter cubed will be 1 meter cubed. This one is the same as 1 million. Okay, 1 million centimeters cubed is equivalent to 1 meters cubed. But we know that 1,000 cubic centimeters is equivalent to 1 liter. So this will be 1,000 decimeters cubed. Okay, remember, I've said 1,000 cubic centimeters is equivalent to 1 decimeters cubed. So that therefore means that here we shall have 1,000 decimeters cubed, which is equivalent to 1 meter cubed. So 1 decimeter cubed is therefore equal to 1 over 1,000 meters what? Cubed. Or in other words, 10 to the power of negative 3 meters cubed. So if you are given the volume in decimeters cubed, to change it to meters cubed, you multiply it by 10 to the power of negative 3. If you are given the volume in centimeters cubed, then to convert it, that means we shall have 1 over a million, which is the same as 10 to the power of negative 6. So that volume in centimeters cubed, you multiply it by 10 to the power of negative 6. Pardon me here. I'm not going to find a mass here. I'm going to use this ideal gas equation to find, because the gases that are given are this side. And since the volume that is given is for the oxygen here, then I'm going to find the number of moles of oxygen. Okay? Number of moles of oxygen. This one is going to be equal to, remember this one here, N is going to be equal to PV over RT. So the pressure is 1 times 10 to the power of 5. Okay, it is given here. And then V, the volume, is given as 1.06, then times 10 to the power of negative 3. Okay, remember we are changing it to meters what? Cubed. Then we divide by R, which is 8.31, then times the temperature is 850. It was given already in kelvins. Okay, then what do we get here? We have 1 times 10 to the power of 5, then times 1.06 times 10 to the power of negative 3. Then down here we have 8.31 times 850. This one gives us 212 over 14127. Let me leave it exact. 212 out of 14127 moles. Now I'm going to use the reaction mole ratio, okay? Because we are looking for the mass of nitroglycerin, which is this one here. Now, when you look at this stoichiometric equation, 4 moles of nitroglycerin give 1 mole of oxygen. That means if I have the moles of oxygen here, to get the moles of nitroglycerin, then I will multiply this one by 4. Okay, so we shall say that moles of this nitroglycerin, C3H5N3O9, shall be equal to 4, then times this 212 over 14127. Okay. Then after that, of course, you know that to get the mass, okay, then the mass, we shall get the number of moles, then times the MR. Okay, so we need to get the MR. So MR of this nitroglycerin is going to be 3 times the 12, then plus 5 times 1 for hydrogen, then 3 times 14 for nitrogen, and then we have 16, then times 9. So what does this one give us? 3 times 12, that is 36, then plus 5, then plus 3 times 14, which is actually 42, then plus 16 times 9. Altogether, we get 227. 227. So meaning mass of this glycerin here is going to be equal to the number of moles we got, 4 times 212 out of 14127, then times the 227, the molecular mass. So what do we get here? Now this one I'll multiply by 4 times then 212 out of 14127. And then to 3 significant figures, I'll write it as 13.6. 13.6. Roman 2, calculate the total volume of gas released by this decomposition at 850 kelvins and 1 times 10 to the power of 5 pascals. Now what we need to do here is to go back to this stoichiometric equation and we look at the total number of gas molecules. We can see 12 here, we can see 10 here, we can see 6 here, and then 1. So when we add all of this together, I'll come here and say total gas moles, or total number of gas moles is going to be equal to, there is 12, there is 10, 6, 1, then 10, then 6, then 1. This is 17 plus this, I think that is 29. So that is 29. That means the total volume of gas is therefore going to be equal to 29 times 1.06, because for oxygen, we saw here that it was 1.06, okay? And this is 1 mole here. That means how about these other moles? And all of these gas moles are occupying the same volume, okay? 1 mole of a gas, just like we can say occupies 24 liters at room temperature and pressure at RTP. You see that? So all of these ones are in the same composition there. So we just say same conditions, which we just say 29 times this one here. So what do we get? 29 times 1.06. This one gives us 30.74. 30.74. Part C. Fats are compounds made from glycerol and unsaturated carboxylic acids. 4-pentanoic acid is an example of an unsaturated carboxylic acid. Roman 1, give the molecular formula of 4-pentanoic acid. Now, the molecular formula shows the exact number of atoms that are present in a given compound. But then the empirical formula shows the simplest whole number ratio of the number of atoms that are there in a given compound. So here there is a carbon, okay? So how many carbons are we seeing? 1 here, there are 2 here. In other words, this one is the same as saying CH2, CH2, COOH, okay? Then you bring to this carbon here, then the hydrogen, then a double bond here, like that. So this is what you are actually having. So how many carbons? 1, 2, 3, 4, 5. So there are 5 carbon atoms. How about hydrogens? 1, 3, 5, 6, 7, 8. So those ones are 8. We shall have hydrogens, they are 8, and then oxygens are 2. So oxygens are 2. And that is that as the molecular formula. And then next, draw the repeat unit of the addition polymer that can be formed from 4-pentanoic acid. So for the addition polymer, we just see this double bond breaking down. Okay, so what we can do, I can actually put something like this here. I front these two carbons here that have gotten the double bond in between them, and then here you have the CH2, the two of them, and then the COOH, and then here. So when they are forming the polymers, this one opens up this way, and then this one opens up this way. So then what do we get? A carbon here, and then another carbon here. Then there is a hydrogen, and then a hydrogen, and then here we have the CH2, okay, COOH, or if you want, you can write it like that, no problem. And then here we have a hydrogen, then this one opens up, and then you can even make these ones dotted because they show continuation of that. So this is the repeat unit of the polymer. If we do like this, and we put an N here, that means there are many molecules of this one, okay? But don't put that. When you put the N, it implies that you are having a polymer. Just leave it like that. Okay, then Roman 3, unsaturated acids are often brominated before being added to soft drinks. Complete the mechanism for the addition of bromine to 4-pentanoic acid. Include the structures of the intermediate and the product of the reaction. Include all charges, partial charges, lone pairs, and carrier arrows. In the mechanism, R has been used to represent this group here. Okay, now, first of all, the bromine you are having here, since these are two bromine molecules, they are all electronegative, right? So they try to pull the bonding electrons towards themselves. So by doing so, because they have the same electronegativity, then the dipoles cancel out. So it is a molecule there without any charge. However, as it draws nearer to this molecule here, because of this pi system, which is rich in electrons, which are negatively charged, the electrons here are going to repel the electrons around this bromine here to go far away from this way. So this bromine here will appear to have lost electrons and therefore obtains a partial positive charge. Then the electrons which are pushed away from it come to this other side, and then bromine here appears to have received electrons, so it attains a partial positive charge. Okay, so they attain these charges by induction. You see that? Now, the electrons move from here, and then they come to this one that appears to have lost the electrons. You see that? And then this bond is broken completely. So we are going to have, I'm also going to leave it as skeletal. Okay, so there is a carbon here, and now we shall have a hydrogen here, and then here we are having a bromine. Okay, then we continue here, we have an R, then there is an an H here, then there is a positive charge here. This is now a carbocation. Now this one that has been broken off from here is going to come, it's now fully negatively charged, it has received all the electrons, and then he uses its lone pair then to give to this carbon here that appears to have lost the electrons. Then we have a hydrogen here, and then a bromine here. Okay, then what else are we going to have? So let me have this hydrogen here, a hydrogen here, and then the bromine, then this one here, then you have the R, and then we have the bromine, and then the hydrogen. Okay, but now better I put I can put the carbons here. Okay, because if it is skeletal, then I'm not supposed to show these hydrogens which are directly attached to the carbon. So I can put my carbon there, and then here, and then there. just like that. Then D, a reaction of another unsaturated carboxylic acid T is shown here. T is one of a pair of geometrical cis and trans isomers. Draw the other geometrical isomer of T and explain why the molecules exhibit this form of isomerism. Okay, since this one is a double bond, we can see that here there is a silent hydrogen. Remember, the hydrogens which are directly connected to the carbons are hidden in the skeletal formula. So here we are not seeing a hydrogen, because usually when you are having this cis and trans, you can have an identical group. Let's say this one is the hydrogen here, maybe this one is the hydrogen. But in this case, we are not having, all the groups are actually different on these two carbons that are in the double bond. So we are taking this as the big group and then another big group. So if they are on the same side, then that is cis. Okay, then the smaller ones on one side, that is trans. I mean also cis. Okay, and then if I get this smaller one here and then this other smaller one here, then take this bigger one here. In other words, you have a big this way and then a big down here, or smaller here, smaller here. So something like that. Then that one will give us the trans. So this one is the cis. Then my trans is going to be, I'll put this double bond here. Then I'll leave this one here, C6H13. Then this one is Br here. So my hydrogen is here, okay? But I'm not supposed to show that hydrogen. And then I will now put this COOH this side. Like that. That will be my trans, okay? This is cis. The first one here is cis, then this one is trans. Then we have to explain why the molecules exhibit this form. We shall say the two groups, there are two different groups on each carbon atom, in the carbon to carbon double bond. Okay, in the carbon to carbon double bond. Then the other one that is very important is no, or you can even say restricted rotation about the carbon to carbon double bond. Okay, because of the pi bond, remember there is sideway overlap of these orbitals. So there is this head-on overlap, so to form the sigma bond, okay, that one there. Then these ones here are going to overlap sideway, and then they form that circle. So the electrons will be in position to move from this way and then this way. So they form that circle there. So the rotation becomes limited, okay, on that double bond. So that's why we say no or restricted rotation about that carbon to carbon double bond. As simple as that. Roman 2, identify the reagent used to convert T to U. T to U. When we look at this one is unsaturated, but then now here it is saturated. That means they added a hydrogen here and a hydrogen here. You see? So that is, of course, hydrogen. We can put hydrogen gas maybe under nickel as a catalyst. So I would just put hydrogen. As simple as that. Lastly, Roman 3, the carbon to bromine bond has an absorption between 500 per centimeter and 600 per centimeter in an infrared spectrum. The infrared spectra for both T and U have absorptions between 2,850 per centimeter and 2,950 per centimeter. These correspond to the alkyl groups, the C2H bonds. Identify two other absorptions that would be seen in the infrared spectra of both T and U. One other absorption that would only be seen in infrared spectrum of T. For each absorption, give the range of the absorption and the bonds that correspond to these absorptions. Okay. Now, back then, they used to give what we call the specimen data booklet, which actually looks like this. Specimen data booklet looked like this. Now, let's go to those absorptions. These are the ones here. The characteristic infrared absorption frequencies for some selected bonds. Now, when we go back to our question here, let's check where there is T and U. T is here. What is common? There is this carbon here, double bond to then the OH. Okay, you see that? It is common for both of them. This group here. So we must see an absorption here. Okay? We must see an absorption here. And another one should also be on this OH here. Okay? For the carboxylic. So I will go to my table here. So from here, we can see this one here, C2O. So I can pick this one here. Okay? That is the bond, let's say for ketones, and of course we don't have esters, neither do we have amides, so I can pick for ketones. But we can see that actually this one comes from the carboxylic acids, right? I think this is carboxylic. Yes, we can see carboxylic acids. So what I can do from here is to use this one here. We can take, there is C2O. Yes, there is this one here for alcohols, ethers, esters, but even carboxylic acids are not there. But so long as there is C2O. So there is 1040 to 1300. That is for both of them. Okay, it is there. Remember, here you have the carbon, the double bond, then there is this O, and then the H. So we are talking about this. So here we can have an alkyl group to give us, let's say, the ester, or it is the ether, if this one is not there, and you have an alkyl group here. So like that. So meaning, I'm going to write here, and I say for both of them, in both, so I will say absorption, absorption 1 present in both. So I will say at, let me not repeat the statement. I will just say at 1040 to 1300, okay, per centimeter, because of carbon to oxygen. Okay, then in both, again, we can see the carboxylic acid, right? The COO here. So when we go back here and we check for carboxylic acids, you can actually see it here. So 25 to 3000. You see that? Okay. So that is what we are also going to write. And then we say that there is one at 2,500 to 3,000 per centimeter, okay, because of the RCOOH group. Okay, then absorption only present. The other one could be from this data booklet here. This one here, I would take 1670 to 1740. Okay, but you find that in the scheme, they can give you something like 1680, then to 1730. So these values used to change, some of them used to change based on the data booklet they used to provide. You see that? So, but let me stick to the ones that have been the same all through. Okay. So I've used this one here and then this other one here, the CO. Okay. So that is that. Then we can go to the next one, the one that is only present in T. So let's look at T. T here has gotten a double bond here. Remember, BR is common. This one is common. You see? So we have the alkene here. So it is the one. So when we go to an alkene, where do we see it? For alkene, it is here, 1500 to 1680. Okay? So I'll go back here and I say that the absorption has to be at 1500 to 1680 per centimeter because of the carbon to carbon double bond. Okay, so that is that. So this has been it for this paper. Thank you so much for watching. May God bless you. If you find the content very helpful to you, kindly like, share, and even subscribe. See you in the next videos.